More recently, he's been working in two main areas, one in resource efficient learning for large foundation models, and the other one for marrying deep models with traditional symbolic decision making, which we'll be talking about today. So please take it away.
Okay, cool. Yeah, thanks, Yisong, for introducing me. My name is Yuandong Tian. I'm a research scientist from Meta AI, FAIR. I've been working on many different directions. This morning, I actually gave a talk in Caltech in Georgia's class about understanding transformers, understanding neural networks. And we have a understanding to basically to actually improve the existing systems for training efficiency. But that part was not covered because of time limitations. And the second component that I've been working on is the decision making. Right? So how can we leverage deep models in order to make decision making much more efficient? And how can we make AI guided design much more reliable and useful in many different scenarios? Right, so I think today I'm going to talk a little bit about the second part. So let's start from there. So we all know that large model has been taking over the world. So have been used in many different scenarios since 2022, 23, right? So people start to use it for content generation, AI agent, AI copilot, summarization, all different scenarios. And I think just today, Meta released the Llama 3. I strongly encourage everyone to use it. It's very strong and also very small as well, and has a huge vocabulary size, and can be used in the different scenarios. Right. So everything sounds very good, right? So and then people may ask about the question, what large model cannot do well yet. Right, so people actually ask about this question because we want to make the model stronger in the future. People also want to ask about problem because we want to understand what's going on inside larger models, right? So there's a lot of different questions we really want to think about. So here I'll give you one example about the task called travel planning. So this example actually was brought about by one of our previous paper called Travel Planner. It's a joint collaboration with Ohio State University. And in that paper, we actually find there's one benchmark we construct so that even the most state-of-art model cannot do very well. So the task is very simple, right? So it's basically we do travel planning. We ask the model to do some kind of planning in the following. Right? So I'm going to maybe Hawaii, different places for 2 days, and I have a budget of $1,000. I want to stay there for 3 days, and I have some preferences in restaurant and also in hotels. And please give me an optimal itinerary. Right? So that's the question that you usually can ask. So what happened here is that for this paper, we have followed this kind of paradigms. We start with some like tool use, right? So we call different tools to get information necessary. And after that, use the information to do planning and also to do search. And finally, there's some plan. The plan is to say, I have to be at some places at day 1 and then take a flight to somewhere else to day 2, etc. Right, so that's the plan. Surprisingly, if you want to use large model to do that, it actually gives you pretty bad performance. Right? So we tested like 2 different kind of scenarios. One scenario is that okay, we just like the model to do everything for us. Right? So what we do is like we ask the model to use the API we provided to call all these informations and then use the information to plan the travel. In these situations, you're going to see that the GPT-4 Turbo is going to give you 0.6% of accuracy. It's basically very, very small. It's less than 1%. So in many cases, it doesn't really well. It doesn't do very well. And there's another way of doing evaluation. It's called soul planning, in which we already provide all the ground truths tool use, and which means that the ground truth tool use give you all the information that you need in order to plan optimally. And then we ask the model to plan the travel. Right? So this actually give you slightly higher numbers, which is 4.4%, but still very, very low compared to humans. Right? So this actually give you this kind of like idea that still we cannot do good solutions that satisfy many constraints yet. Right? So I think usually one symptom that you actually see is that the large model will try to find a solution that is good for one of the constraints, but not the others, right? So we will forget about, oh, I should satisfy budgets and satisfy the dates and satisfy, for example, the hotel preferences, etc. So it's actually a hard problem to deal with. It's also a very hard problem for reasoning as well, right? So another example I will give you is that this kind of a very simple example, and people often use in Twitter, in X, to discuss about limitations. This is about like how can language model solve the tic-tac-toe problem. Tic-tac-toe, we all know it's a very simple game, and people play stones in this 3x3 grid, and whoever get the first three stones line up in either horizontal, diagonal, and vertical wins. Right? But unfortunately, if you play this with Cloud 3 Opus, which is basically starter art approach, it doesn't really do very well, right? So basically, for example, this one, it actually realized it seems like this is a draw. Actually, it's not draw, because given the bars, like where are the bars, you can actually see like I'm going to pick an X on the top. Bottom left corner, we're going to win the game, but unfortunately, the representation in the larger model does not really see that, and they see it's a draw, right? So it's actually a big problems, right? So and also for the example to the right, you also will see similar situations, right? So it's you realize that the model think, okay, I placed an O stone to the left in order to block attack, but actually the attack is not happening on the leftmost vertical lines, but on the middle lines, right? So you can still win the game by placing a stone at the bottom middle line. Right? So it's very clear that still the state-of-art model cannot do things very well. Okay, so then like how we can deal with that, right? So is there a way we can make the model stronger and more efficient? So there's several different ways of doing that. So in this lecture, I'm going to talk about three different parts. So the first part is about how can we leverage existing solvers and using this solver to provide data and use data to train a deep model so that the model becomes stronger, right? And the second is that maybe we can actually train a system that is end-to-end differentiable, combining solvers and deep models so that the system may become very capable in having good solutions that satisfy all the constraints there. And finally, there's another case that we can actually find some analytical structure of the solver solution, and we can use deep models to simulate and also to basically fit this analytical solution so that it will give you a better solution and in lieu of the solvers. So I'm going to talk three different parts in this presentation, and let's go one by one. Okay, let's start with the first part, which is the better transformers with data from solvers. And the traditional solver actually did very well in different tasks. Right, so for example, the tasks with maze navigation and also with SurCo, what people usually do is that okay, forget about reinforcement, forget about everything like that. We just check like what's the check basically put everything into kind of symbolic form, and you call the source, and the solver will automatically give you a path, right? And that path will give you optimal solutions using, for example, A star or different kind of planning algorithms. Right, it's very simple. So you don't need any knowledge on reinforcement on like larger models. So on SurCo task, the goal is here is to actually put the two boxes into the two destinations, right? So but you can only push the box, but you cannot pull it. Once the box trapped into a corner, then you are dead. You have to backtrace and you find what is the best way to put all the boxes into that destinations. So for this task, you can also find a way using solvers to solve these problems. Of course, like the larger the problem is, the complicated it would be, right? So it also depends on like how you're going to write the heuristic functions in order to make the solver much more efficient, right? So for these tasks, usually for transformers, it does not work that well. But in our paper, we actually come up with an approach that can actually increase the performance of transformers substantially and also reduce their data usage by using the trajectory or the search dynamics that is being created by the solvers. Okay, so let's start with the very basic stuff, right? So let's say how the solver works in these kind of scenarios. right? So first of all, you might start with this kind of very simple cases. You are having starting point and also goals, right? So and then you may have two walls, right? The wall is one is in 2, 1, and the other is in 0, 2. And your goal is to find what is the optimal path from the starting point all the way to the goal. So if you call the solvers, you actually will have a few paths that you can, yeah. So wait. So you can basically do, right? So you start from this starting point, and then you create states. The state is 0, 2, which is starting here, and then you close this the text, the states, and then it will actually goes to 1, 0, right? So from starting from here, you can expand your tree all over the place. You can expand to the left, to the right, or you can expand to the top, to the bottom. If you expand to the right because there's a wall, okay, you know that your expansion fails, you won't expand there, but you can expand downwards. So it will create another nodes, right? So you can also close that node and keep expanding. So here you can expand two different directions, right? So it can expand to the right or expand to the bottom. And this will create two different states. And then you can continue doing that until you find that one expansion actually leads to the goal, right? So once you find that one expansion leads you to goal, then what you can do back tracing. You actually will find optimal paths from that, right? So basically, this is the optimal path, and this entire procedure is called the search dynamics. So you basically follow this breadth first or whatever heuristics in order to create a sequence of nodes until you actually find destinations. Right, so it's very clear. And what we actually do here is that while the solver can give you this sequence of trace and then optimal plan, we can actually train a transformer model. And transformer model will basically take the prompt, which is basically the description of the language, of description of the environment. Right, so TA is the description of the environment. This basically says, oh, it starts from the starting point is here, 0, 2, and the goal is the 1, the 1, 0, or 0, 1, and the wall, there's two walls here, and this is the description of the environment, and the trace for this entire search, and the final optimal trajectories, right? So that's basically the idea. And then you can basically train a model called search augmented models. Right? So here basically there's a comparison. So if you just do prompt and plan, this is basically called a solution-only models. The model does not really go through the trace in order to predict the optimal plan. But the model basically take the prompt, which is the description of the environment, all the way to the plan without any intermediate tokens. Right? So this is called the solution-only models. And the other is called the search augmented models, in which when you are training an autoregressive transformers, you starting from this prompt, you first predict the trace, and then given the prompt and the trace, predict the plan. Okay, so that's basically the idea. And how you're going to do this training, we are actually using an encoder-decoder structures. So we first use a prompt to encode, and you get a representation of the prompt. So the prompt here, it basically represents the environment. And once you have the representation of it, and then you use decoder, which is also autoregressive models, to plan recursively until you get either the plan in the search only model or the trace and the plan in the search augmented models. So that's basically the way we are training the models. And so this is basically give you like how many tokens you will currently have. So plan only, it only will occupy 100 to 400 tokens. But if you do trace and plan, usually this will be much longer because the trace is often taking a long time to generate. Right. So, but interestingly, you actually see there's actually interesting curve. This is kind of scaling curve. Right. So our search augmented model is much more data efficient and also parameter efficient. Here, if you just use a search-only model with 175 million parameters, the curve look like that, right? The performance is really bad at the beginning because you don't have enough training sequence. You really get to almost close to 100% for 30 by 30 mate task when the number of training sequence reach 1 million. Okay, that's the baseline. However, if you try search augmented models, even with just 15 million parameters, you are able to get very high performance, even with very few amount of data. Right, so it basically starting from here, and then of course the model will become better when the data they become like larger, right? So that's an interesting behavior here. Right, so it's, and also it doesn't really matter like what are the how many parameters we have. Right, so you have like a large parameters and still performance are reasonable good. But if you compare this with the search only model, of course, it's more data efficient, and at the same time, it's also parameter efficient as well. Right, so in some sense, it can be regarded as a kind of advanced version of chain of thoughts. Right, so question.
Sorry, so I'm a little bit lost here. So when you're doing A-star, you got to provide that the heuristic is also consistent and admissible. Are you providing the heuristic over here, or is like transformer learning the heuristic from planning or creating, or are you giving the heuristic to the space?
Yeah, so here we basically train the model with A-star trajectory. So A-star trajectory is created by a specific heuristic.
Okay, and so that same heuristic is being
Fixed.
fixed. Okay, so the heuristic is being fixed.
Yes, it is fixed.
Varying the heuristics.
Yeah, so this is going to be the next step. Yes. So varying the heuristic definitely can be important. And we actually did some small experiments, but not systematics. It doesn't seem to be changing a lot. Yeah, I think that's some magic here. We don't really have a clear idea. Right? So there's some performance drop. Maybe this is because there need to be some tuning in terms of the parameters, to get things better. Yeah. But we are using the same parameters here. Yeah. Okay. If there's no question, then we can continue. So on SurCo, we actually get the very similar curves. Right, so if you start from small models, the small models with search augmented, you actually get much better performance. Right, so with the search only, solution only model, the performance is worse. Right, so of course that's the kind of trend.
I have
Okay.
a quick question.
Yeah.
So when you do this trace rollout, the
Yeah.
transformer's context window can actually attend over the entire trace.
Yes, exactly. Yeah.
So I was wondering how you like generate.
Yeah, we run them multiple times.
How many times?
I think it's for like, it should be 3 times. Yeah. But we can definitely do more. I mean, the reason why it's not touching, so this is a missing data point here, is that if you have large parameters and also the context window is huge, then you might spend a lot of time on that. Yeah. This is all actually the cons of the approach. Yeah. Okay, so now we know like, okay, seems like this kind of models can do very well in terms of interior learning when we want to use few data in order to get optimal plans. Right, so I mean, then the next question is how to go beyond, right? So we don't want to just do material learning. We want to do something that is more exciting than that. Right, so then we actually go to the second stage, which is the fine-tuning stage. So in terms of the fine-tuning stage, what happens is that we really want to make sure that the model still can output an optimal plan, but you want to get optimal plan with shorter trace. Right, so basically you do fine-tuning in this kind of loss function, with this kind of reward functions. The reward function basically tell you, okay, the shorter the trace is, the better it will be when you train the models. So this is actually called a Searchformer. That's an improvement of the search augmented models, which is basically by imitation learning. So it's interesting to see that the Searchformer can actually do even better than the search augmented models. Right, so we can basically do this Searchformer in multiple iterations. So for every iteration, we are doing a called expert iteration. So we use the current search augmented model to generate all the traces and also their plans and pick those traces and a plan in which the plans are optimal, but the traces are shorter than basically the baselines. Right. So the reason why we can do that is because the search augmented model is trained on non-deterministic version of A star. And so that every time the trajectory is different, but it will lead to optimal plans. And second, the circular optimal model can be generated in an autoregressive manner, and by varying the temperature, you will get different traces at different generations. So and for these different traces, you pick one that is shorter, but still give you optimal plan, and use this amount of data to retrain or to fine-tune the Searchformer for several steps. And you're going to see that after several steps of training, the average sequence length per test task actually gets shrinked, right? So more and more and more. So that's actually good. So this means that it actually find some algorithms that is shorter in terms of in terms of the trajectories in order to get the optimal plan. Right? So that's a good thing. It means that the algorithm actually finds something that is new than A-star search. Any questions?
So can you like train like a neural network or something like which can give you the symbolic representation of this kind of heuristic, which is kind of better than this A-star's fixed heuristic?
Yes. So that's and this is some numbers, right? So if you start with the search augmented models, right? This is basically the number of solutions, number of trajectories. You can think these are solved. But so by solved, we mean that trajectory may not be optimal, but it's feasible and it's actually can solve the problem. Right? Optimal means that the actual output plan is optimal. Right? So note that the optimality score is less than 100%. Because for all these transformer-based models, there's no guarantee about optimality. So of course, there will be some probability that some of the final plan is not optimal, but that's fine. As long as it's differentiable, then we can use different fine-tune method to make them even better. So you can see that after 3 steps of the fine-tuning, the amount of solved cases actually getting higher, and at the same time, the optimal also getting higher a little bit. So and this is you can see this is actually comparable to a model that with solution only. So this is in some sense pretty nice. Yeah. Okay, so and this is in SurCo bound task. And we can also test like whether the actual bootstrapping will actually reduce the length of the intermediate trace. Right, so this is basically in order to measure that, we define a metric called improved length ratio, IRR. So it's basically very simple. Basically, you have your current ratio, the current like search length, the search dynamics length, in terms of tokens, number of tokens, divided by the dynamics length that is computed from A-star. So this number should be greater than 1. I mean, if it's larger than 1, it means that we're getting like a more efficient search results. So I mean, every iteration you see like the ratio become larger and larger, which means that we somehow find a way to reduce the search trace. At the same time, we still get either solved plan or optimal plan. So that's a good thing. Yeah. Okay. Any questions?
Yeah. So in the previous slide, you showed like that when you shorten the paths, it gets slightly worse. Is there some sort of pattern to the paths that it gets wrong? Like how close are they to the optimal path? Yeah.
So we actually have some study on like the failure cases, right? So in some cases, the reason why it goes wrong is that the transformer seem to misremember some of the performance specifications, right? When they say, oh, here's actually a wall, but actually find a pattern across the wall. This is kind of as infeasible, but there's some like embedding issues in the representation. Yeah, that is the one. That's one way you can see that. Yeah, and in some other cases, it does not really give you optimal solution because it thinks like a one block is actually a wall, but actually it's not a wall. It's actually possible paths. So by doing that, you actually you won't be able to get the optimal paths. Yeah.
So I think I have a question. So then basically you're saying you're getting because you are predicting traits, but you're not actually verifying traces just by predicting and getting results is kind of the plan. Is that my correct?
So you want to predict the trace so that it becomes shorter, but at the same time you want the final optimal plan is still optimal. Final plan is still optimal.
Right, but your test like what do you do?
So for this one, we don't have any specific form you want to follow. You want the trace to follow. You just want it to be shorter. That's the goal.
So basically, in the first version, it
just like if we're saying that the model predicts it and then
Yes.
Am I-
Yeah.
Yeah. Okay. Thank
Yeah.
you. Makes sense.
Yeah. So basically, we don't really know like what is the shortest trace should be, but we just say that the trace should be shorter and shorter.
But is that invisible trace? It's kind of
Yeah. So I think that that's like the question. That's because there's no guarantee in terms of A star, right? So so I won't say it's admissible. It just like give you a better way of planning, but it's possible that the planning may not be optimal, may not have guarantees. In the future, there may be a way you can ensure a single guarantee. Yeah. 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 Right now, that's the case. Yeah. Okay. So that's the first part. And the second part, I'm going to tell you how we can train deep models with solvers. That part, we actually have a series of work collaborating with University of South California about how we combine solvers with deep models together. So for this one, we basically want to like think about a little bit on like industrial kind of problems, right? So so think about like we want to optimize nonlinear objectives, but with combinatorial constraints, right? So here's like a figure demonstrating what's happening. Right? So you have some nonlinear function, like arbitrary nonlinear function that's maybe complicated. And then if you just want to find our optimal path, optimal trajectory, optimal like points, maybe that's fine. You can just follow gradient descent. But you have constraint. A constraint basically say, oh, you also have feasible region that is specified by combinatorial equations. Right? So this might include, for example, linear constraint, nonlinear constraint, or maybe even like integer constraints. It's called combinatorial constraint. But for this kind of problem, it's very tricky to get a solution because you cannot use, you can use, for example, general nonlinear optimization, sound like, for example, like evolutionary algorithms, right? But evolutionary algorithm is very slow. It takes forever to get any solutions. And plus you also want some feasibility, which is also pretty complicated. And on the other hand, this kind of problem actually has very many real world domain applications, right? So if you think about like AI guided design in many different domains that is going beyond large language models or CS department, then you actually see many problems like that, right? So you want to do planning in this kind of complicated situations and everything is nonlinear, but you also have constraint, right? So in order to get things to work. So you have lots of problems like that. So in this case, what kind of thing we can do, right? So here's one example. The example is actually happening when we actually want to run a training for large models, right? So here is the example is here. So it's very simple. You have k tables. Each table will be put into n GPUs. So this device is actually GPUs, and you want to put k tables into n GPUs so that each GPU will have memory capacity, and you don't want to go beyond this capacity. And at the same time, you cannot split the table into two parts. You can either place table in GPU 1 or GPU 2, but not either of them by splitting this table into two. So that's basically the constraint. And the final like objective function, the latency, is actually a neural network. It's a nonlinear nonlinear cost. Right? So then it's become in some sense very complicated. Right? So here's the formulation. Right? So Xij means like you put table X to device J. Right? So this is the demonstration of Xij. Of course, Xij has to be binary. You cannot split the table into two parts. It's binary. So, and sum over J, Xij has to be 1 because a table has to be placed somewhere. So the summation of across all device has to be 1. And if you place the objects into each of the GPUs, and the capacity cannot be exceeded, right? So if you sum of I is all tables, sum of I on their memory requirement, then the summation has to be smaller than or equal to some capacity MJ. So that's the constraint. And the object function is nonlinear because it may have a lot of communication costs or different nonlinearities due to caching, loading, etc. So this is can be estimated by in industry designs. So you can see the problem itself has combinatorial constraint, it has nonlinear constraint, it has a linear constraint, and it has inequality constraint, and it has basically binary constraints. So for these problems, right, if this loss function is linear, then you can actually call existing solvers. Right, so we have a lot of solvers already on the market. Right, so GNUB is one. I mean, Skip is also one. They have been engineered to death for decades, so that the performance is super good. You can actually call them in short amount of time, and it will give you a solution. A solution will be useful for your problems. Right. So what happened to nonlinear case? Right. So if this error is really like some complicated functions, if the error function has some analytical form, right? So error has some kind of form, say it has to be log, exp, whatever. Then it's possible that you can still call solvers. There's a nonlinear solver that try to leverage the property of each functions there to set up a upper and lower bound in order to do branching. But you can definitely do that. But if the error is actually estimated by a neural network, then what can we do? So usually this is the kind of problem that people cannot deal with. So in our paper, we actually find a new way to do that. It's called SurCo. And that paper actually is last year's NeurIPS, and actually one outstanding paper in one of the workshops about discrete optimization. So what the idea is about is that the original problem is nonlinear, right? So you have an f function that's nonlinear. X is the domain that you want to optimize, and Y is the problem specification. So Y may mean that the memory capacity of each GPUs, how many GPU you have, etc. And this basically is an optimization, but X subject to some combinatorial constraints. It's hard to solve. But what we can do here is that we can actually predict a surrogate cost, C. That C is a function of the problem specification Y, such that with the surrogate cost, the problem become linear, and then you can solve that with existing solvers. Right? So I want to say that again. You want to find a surrogate cost C so that the solution you obtain from the surrogate optimization also minimize original problems. Yeah.
You're basically predicting which surface of the polytope the solution is likely to be at.
Yeah, so to some extent, yes, but we basically leave the machine learning to figure out.
Sure.
Right, it's possible that the exact polytope is hard to predict, but you can predict the rough direction.
Yeah.
So that the solver will take the rest of it. Right. Yeah. Okay. Then that's the challenge is how you find the right objectives. Right. So and what we can do with that, how we can actually deal with that, we can actually do gradient descent in order to get the solutions. So here is basically the surrogate learning, how the learning is done. Right. So you actually have this kind of computational pattern. So it starts from some surrogate cost C. That C will go to the solver, and the solver will basically go to the solution. The solution, you put a solution into objectives, and you want to minimize our objectives. Right. So you have the computational graph. But for the computational graph, what we can do is, I mean, if you ask anyone from PyTorch team from any kind of deep learning area, you say, okay, backpropagation. Right. So that's what it is. So what we do is we backpropagate all the place, right? So you assume that a British function is differentiable, so you can backpropagate, you get gradient here, and then the solver can also be differentiable by having by basically using different tricks. So for example, the simplest trick will be you can do some finite difference, you can get gradient from it. But people recently in recent paper they actually show you don't need to find difference. You can actually do just one pass of solver, you get a gradient as well. You can do backpropagation. Then you actually get some kind of gradient with respect to C, the constant coefficients. Then you can basically do this iteratively on the fly, and then you automatically get a coefficient C that will lead to a solution that minimize objectives that may be non-convex. Okay. So that's basically the idea. And this is called a circle zero. Why it's called circle zero? It is because there's no neural networks. Right, so everything is, I mean, F is fixed neural network, so we treat this as a the kind of smooth functions, and there's no neural networks, right? So you basically learn everything on the fly when a new optimization problem comes. But now you can do something better, right? So you can do circle prior. What I mean is that you, instead of learning this coefficient C, you can assume that C is actually coming from a neural network, another neural network, and you actually backpropagate through that neural network in order to get its own parameters. Right. So the reason why we want to add another neural network is that you want to generalize across multiple problem descriptions. So given the current problem description Y, you figure out there's a C that can be useful for surrogate coefficients. But when in the future, there's a new problem description, y prime, what happens? Right. So if you follow circle 0, then you have to do backpropagation again. That's not efficient. But if we already have a neural network, and we can actually train this neural network in, for example, 100 problems that we already know, so that the neural network actually have a coefficient, have a parameter theta that can correctly predict the right C, and then you can use the neural network for new problems that have never seen before. So this is what's happening here, right? So you have for example, 100 problems with the corresponding yi is the problem descriptions, and then you can train this. Note that for all these 100 problems, you don't even need to know the optimal solution. You just keep training because it will automatically figure out what is the optimal solutions in the training procedure itself. Once you train this model, then you have a good theta. So this theta has been learned. So you have a theta here. So once the theta is here, then once you have a new test examples, y test. So y test is the kind of the description of the test. You plug this into the neural network, and combined with the learned parameter theta, you will actually give you a test coefficient C. That's likely to work reasonably well. And then you can plug this C test directly into the solver, and it will give you a solution. A solution is very likely to be a good solution according to the parameter distribution. Right? And finally, you can combine these two together. Right? You can say, okay, you first start with this C0, which is basically predicted by a y test. And once you have the C0, and you can keep doing this circle 0 kind of backpropagation to basically continue improving the surrogate coefficients to make the objective function even better. So that's called the SurCo hybrid. Any questions? Yeah.
I thought the original motivation was that this problem was
Oh, yeah. So there's two components. First of all, it's whether it's feasible or not, right? For the feasibility, you can actually prove it's feasible because any solution that comes out of the solver has to be a feasible solution. So that part is guaranteed, right? And the second part is this F function, because it's convex, non-convex, it's complicated. We don't know. What we only know is that this F function, as long as it's small, we are linguistic. Yeah. Okay, cool.
I couldn't hear the question, so maybe it's the same answer. So what is the benefit of learning the conditions as opposed to the solution, right? Is the ability to satisfy the constraint?
Yeah, so first of all, it's a way to satisfy constraint, because if you go through the solver, then it's guaranteed that this X star always satisfies all constraints, right? So if you predict this X directly from your network, then it will take a long time for you to get this right. Because you have to put out negative samples. You have to basically set clear boundaries, and at the end, you might get like maybe 90% of solution correct, but 1 to 10% is not correct. Right, that's the first thing. The second thing, I think that this is also an answer to Yisong's question, is that if you want to, for example, this is a figure that shows intuitively what's happening, right? So, for example, the optimal solution is in the star, but if you go through the solver, then we don't need to precisely predict the optimal solution. We just predict some kind of direction, rough direction. Okay, this is the direction that roughly you can find. That direction may be much easier to predict than the actual optimal solution you want to predict. Right, and then you basically rely on the solver to correct that, to actually make the solution optimal and also feasible. Yeah. Okay, so that's basically the idea. So basically, to recap, we have circle 0 that does not need any offline training data and just solve a single problem instantly on the fly by backpropagation, right? But this might not be efficient. And then you also have a circle prior, then try to use offline data to quickly solve a problem at test time when just one solver call. We train a model with neural network, we get a theoretical, we get a parameter theta, and then we use the parameter to directly predict the C, and you call the solver once, and you get the solution. Or you can do like a circle hybrid, basically, which means that you first do offline training, and then on the fly fine-tuning the surrogate. So you can do both. Okay, so let's go back to this embedding table sharding problem. So that problem actually is the first problem that we met with. This is actually a collaboration with the production group in which they actually have the real problem to deal with. right? So we actually use the public data deep learning recommendation models. And we actually compare this with multiple existing solutions, right? The big greedy is one, which is kind of crappy baselines, but we also compare with state of art, which is actually our approach as well, using reinforcement called Dreamshot. So we actually can see there's actually a difference in terms of, so if let's just do this one. So yeah, so first of all, there's three different approaches, right? So there's a SurCo 0, SurCo Prior, SurCo Hybrid. So these three are actually our approach. So it corresponds to all the like a dot, either like a slash line or horizontal lines, right? So there's two different metrics. One is how good the solution is, right? So you really need the solution to be as small, the loss to be as small as possible. And the second is that you really want the deployment time to be as small as possible, right? So first, the solution, let's check the solution loss. For the solution loss, you're going to see that the SurCo Hybrid and also the SurCo 0, they actually have pretty small loss compared to other approaches, right? Especially when we deal with like larger settings. So here like a 16, 15 means like there's 60 tables you want to deal with. So go from left to right, the size of the table become larger and larger. Right? So and the problem become also a larger scale. So you have this, so these two actually has good solution loss after optimization. And SurCo Prior has a higher loss because it's a one-shot approach, right? So you predict the C and you call solvers and that's it. It will have higher results, but still, this is actually pretty good compared to other baselines. Right? So if you go to the next step, there's the table on the deployment time. On the deployment time side, SurCo Prior is the fastest, right? So a Dreamshot is actually also pretty fast as well because it's also a one-shot prediction, right? SurCo Prior is fast because it just predict the one C and then call solvers, right? So but on the other hand, like a SurCo Prior still has pretty good actual solutions, right? So there's a balance between the two. You can always basically adjust the balance by calling, for example, SurCo Hybrid, but with fewer number of iterations. Right? So you will have basically a balance between the two. Right? And you see that both the SurCo Prior and also this actually give you like a very small amount of time used to deploy. This can be very useful because you really need to make the very important decisions in a very short amount of time in order to move all the tables to different GPUs and to train the models. Right? So if you spend like, for example, like 1 minute to do that, then it's better to just use greedy approach. That's maybe much faster to make decisions, and it may have some extra overhead to train the models.
So the latency is in seconds, or
yeah, the latency is in it should be in seconds. Yeah.
okay. So if the runtime takes, I see the runtime takes 50 seconds, it doesn't. Yeah.
Yeah, I remember. I think this should be no. So this should not be seconds. This should be milliseconds. Millisecond. Yeah.
So because it's using.
Yeah. Millisecond. Yeah. Okay. Cool. Okay. So then we go to the next that design problems. This is another industry design problem that we can leverage our SurCo approach. Right. So for this one, what we do is there's actually a very small device. It's probably 100 nanometers by 100 nanometers. Right. So and the goal here is to design the pattern within this small image so that when the light goes from the top, it will actually change the path according to their wavelengths. That's basically the proportionalities. That could be depending on different design. There could be different kind of tools like that. So for example, this one, by designing this material like that, you can actually bend the light. If the light comes from the left, it will bend all the way to the top. Right. So for this one, it's called a beam splitter. Right. So when light comes from the left, it will be split into two beams of light on the right. Right. So and also for this kind of finally for this one, this is called the wavelength division multiplexer. This means that you have a light with some wavelengths goes from the left. It will depend on the wavelength. It will either go on the top or on the bottom. Right? So people may wonder like why not use some prism to do that. But the answer here is that the size is super small. It's kind of 100 nanometers by 100 nanometers. nanometers. It's very, very small. It's 10 to the minus 9 meters. So you have to design something fancier in order to get this to work rather than using a prism. A prism will be very much larger. Yeah, you can do that. Yeah. Yeah. So and there's a constraint. I mean, you cannot put arbitrary patterns there because there's some constraint on the manufacturing. So each pattern, if you put them there, it has to be at least some size. Yeah. So basically, you can think each pattern can be brushed. Basically, there's a brush, and that brush can reconstruct all these patterns. But really want this brush to have a smaller kind of diameters. You cannot be smaller than that. Yeah. Okay. And the objective function here is actually quite complicated. So you first need to simulate this entire device because everything follows electromagnetic waves. And once you follow that, then you will get spectrums of this device, and then there's some complicated functions in order to minimize so that the device will give you the right answers. So for example, for this one, you really want the wavelength 1 to go on the left, wavelength 2 to go on the right. So in order to measure that, you want to measure like, okay, how much energy you receive here and how much energy you receive there for 2 different frequencies. And then you come up with some complicated loss functions in order to make sure that by maximizing it or minimizing it, your design goal is met. And that's basically the loss functions. And the feasible solution is actually need to satisfy some constraint that it has to be the union of the brush pattern. So there's a brush pattern in the device, in the actual machine, and then the union of brush pattern is basically something that you can actually manufacture by your machines. So this is actually a linear constraint if you write them down correctly. And everything now is become a linear constraint, but with non-convex optimization problems. Right. So then what happens here is that you want to still measure the 2 quantities, right? So one is the solution loss, and the other is deployment runtime. So here, because we are looking for anything that is feasible, so there's a constraint, and also there's a criteria. So as long as it's feasible, then we actually think this is good. So we actually see that the SurCo 0 and SurCo hybrid, they actually do a very good job, and they get 0 loss here, and they get pretty small loss in 2 of the complicated design problems. So if you compare this with baselines. Yeah. And for deployment runtime, I mean, of course, the SurCo prior is the fastest because it will give you the prediction instantly. But on the other hand, the SurCo hybrid is a bit slow, but still faster than existing baselines. Yeah. And also the SurCo price final results is also good in terms of the loss. There's a trade-off. If you run this for sufficient amount of time, it will be good.
Is there like a simpler domain-specific baseline other than pass-through?
Yeah, so for this one, we basically have to ask the domain experts, right? The pass-through is the one that they provide with us. Yeah, so there could be other baselines. Yeah, so if you basically print out the curve, you see like the curve actually much smoother on SurCo hybrid, right? So it actually goes down very quickly, rather compared to SurCo 0. I mean, even with SurCo 0, it's actually converge faster than the original problem.
Just to understand the last graph.
Yeah.
So the solver only gives feasible solutions. What does it mean for the solution to be about?
You mean, what do we mean by the solution to be feasible?
Yeah, because when you introduce SurCo, you have the whole concept of using the solver that it would only give a valid solution.
Yeah.
So what does it mean in this context?
Yeah, so basically this is the criteria for solution to be feasible. Right, so basically the solution needs to be constructed by a brush, which means that you cannot have a one pixel dot.
Yeah.
So if there's a dot here, it has to be at least some size.
But the solver guarantees that you get a feasible solution, right?
Yeah.
So in the next slide, how did you have, why were any of the solutions from SurCo not feasible?
Oh, you mean this one?
Yeah,
I see. I think that this is basically like there's a solution loss. There's some constraint that is feasible, you can guarantee, but some other constraint actually we put into the loss functions. Yeah.
Not all constraints are satisfied.
Yeah. So basically, there will be some solution that is first of all the solution. This is a feasible solution that you can put, but there are some other constraints that need to be put into the loss functions. But in that case, like it's not feasible. Yeah. Okay. Cool. That's a good question. Okay, so the conclusion for this part is that we can actually handle industry level applications with differentiable optimizations, right? So we really need to basically like find like a linear surrogate in order to get high quality solutions to combinatorial non-combinatorial optimizations. And then we have a circle that can be useful for this kind of settings, and we propose multiple settings for circle, including circle prior, circle zero, and also circle hybrid. Okay. Of course, there are limitations. So this is actually this is the follow-up paper that we did last year and published in Europe 2023. This is done by one of my postdocs. And basically, the limitation here is obviously you really need to require the backpropagation gradient of the objective functions, right? So in order to do backpropagation, and the second is that you also want the solver to be backpropagatable as well. So you want these two, and you also want to call the solvers during the training, because maybe sometimes it's pretty slow. So in order to deal with that, we actually have an idea called using another surrogate, a surrogate on top of a surrogate. Right, so you have a surrogate model M, and M actually will cover this this function composition, right? So you have F compose G. This is some function that you really want to optimize. So this is the one that you want to optimize, and then you have another surrogate model M to cover that, and the M can be differentiable. So then you can backpropagate everything through rather than going through F and G in a separate steps. So that's a very simple idea. And how you estimate the surrogate class M? It's very simple, right? So you basically do some kind of sampling in your space, and then you try to match the function shape within the space. And this space is basically constructed by you first like estimate like what is the good theta, which is the parameter for the predicting the surrogate cost. Right, so and within this range of the theta star, and you want to find a surrogate cost, M, which is parameterized by W, regarding to F composed with G. So it's very simple. So then what we do here is like we basically like use existing data to refine this M, and then given the M, you have you use the M to basically learn the thetas. Right? So you do this iteratively. So we have done multiple experiments, including existing experiments of SurCo, but we also do real experiments, which is portfolio optimization. And we all know that you want to find a kind of like a configuration of your stock so that you maximize return. So that's basically the idea. And in this paper, we actually think about like an objective function that is non-quadratic, it's beyond quadratic. So that's in some sense, you want to basically, for example, maximize the screwness or maximize some kind of third order or fourth order terms in order to make sure the portfolio behaves well. But in that case, the loss function will become complicated. And at the same time, you still have the constraint, right? So you cannot buy too much for one stock. So and all the stock, if you add together, has to be summed to your total assets performed, right? So that's something like that. And we actually can see that our approach, which is called a Lancer, can also give you reasonable good performance with fewer number of function calls, right? So I think this is actually understandable because we have a surrogate cost M, and that surrogate cost in many cases can replace the function call, the solver call during the training, right? So but sometimes solver's call may be very expensive, right? So you call a solver, it may take like several minutes in order to get some numbers, right? So in that case, it will be very slow if you incorporate the SurCo pipeline. But with Lancer, because we have a surrogate cost M, and that M actually can give you a good estimate of F composed G, and you can backpropagate through M. You don't need to call the solver anymore. So this actually give you good performance. So you can see that for Lancer, we actually give you, you have fewer number of function calls, while the performance, which is the loss function, actually goes down. Yeah, I see similarly. Yeah. Okay, that's basically one extension of SurCo. There's another extension of SurCo, which is to generate like a diverse solutions. So for design problems, sometimes like, okay, we only want one solution, but sometimes you actually want many solutions, right? So it's possible that we want not only one, but tons of solutions. Some of them, each of them cover a different portion of the space, and you want diverse solutions. But we also want diverse solutions to optimize the nonlinear objectives, and still these objectives come up with combinatorial constraints, right? So you have three components you really want to satisfy at the same time. So it actually makes things more complicated. So what can we do with that? So for this problem, we actually deal with the following loss functions. So the loss function actually composed of this additional group loss. The group loss basically says that I want to also optimize some finalize some design so that collectively they are minimizing some group loss. So obviously, and you also have individual loss, which may correspond to your previous loss functions for previous nonlinear objective functions that we mentioned before. And of course, because we want diverse solution, then we really want generative models, right? So you have now you can put diffusion model, you can whatever generative model in. That models will give you some generation in latent space, and then the latent space, which is basically the design space in our previous nodes, going through a solver, and it will give you a solution. So if you do that, then you actually were able to do some good designs on top of that. So we actually test three tasks. So we still test.
Sir, I did not understand.
Yeah. Okay. Yeah.
So you have a generative model that generates an initial solution.
Yeah. So
in latent space.
Yeah. So the latent space is basically the surrogate space C in the previous slides. Yeah.
Okay.
Yeah. So it will go through a solver, and the solver give you a solution.
So the generative model generates the C.
Yeah. 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 So previously, this C was either optimized or predicted by a neural network.
Yes.
But now, because you want to have a diverse solution, so you really want generative models to generate that.
And then the training of this generative model is you get, like in the next slide, you get like maps from Warcraft.
Yeah.
And then I backprop through the solver to get the C.
Yeah.
And then that I fit the generative model to that C.
Yeah. Yes. That's right. Yeah. Yeah. So for this one, for example, like if you think about this game level design, right? You want the game level design to minimize or maximize some objectives, right? So for example, you want the playing path to be maximized, right? Or you want to, but still feasible, right? So you don't want the game level to be infeasible, which means that you won't be able to finish your goals. But also want your game level to be diverse. You want people to play with like an interesting game level you have never seen before. Yeah. Yeah, so that's basically the task that we can deal with. So, and also in the workflow management and map generation, we want to generate diverse maps. And at the same time, you also want to minimize the paths of each of the diverse maps. Right. So and for inverse photonics, of course, you want to find different designs and all can satisfy the same constraint. And some designs may have nice properties that you might be looking for. Yeah. So that's so we actually test 3 different domains in the paper. The paper is not on the archive yet. It's actually in the it's in the submission site. Hopefully it will get accepted. I don't know. Let's see. Yeah, so there's some results. Yeah, so if you just do GAN plus MIRP, then it does not have any. It basically doesn't seem to be very diverse, right? So you basically like get like a single like basically 1 or 2 blocks there, and it by MIRP being like it actually give you feasible solutions, and there's no very strong diversities. But if we actually use our approach, we actually get pretty good diversities and coverage. Yeah.
Good question.
Yeah.
So in these games, especially if they're complicated games, there may be the maps, the constraints that are active or inactive may themselves be diverse.
Yeah.
For some maps, I want to make sure that it has a narrow whatever, right?
Yeah, that's right, that's right. So it's possible that by changing their constraint, maybe it can be done.
But here, all the constraints are fixed. They're just like the base atomic constraints of this
Yeah.
environment. Right?
Yes. But you still want it to be diverse, right? So for any kind of reasons, right? So for beautiful reason, for reason that you want to find good solutions, something like that. And the good thing about degeneration is that degeneration can actually give you solutions that is guaranteed to be feasible, because everything that is generated is going through a solver. A solver gives you feasible solutions. So this is actually the solutions you can basically like there's several metrics, right? So first is uniqueness, right? So uniqueness means that how diverse it is. If you check, like, find two solutions that are identical, then you have this kind of uniqueness, right? So and these two are actually covering like the trend distributions. And the final one is like a solution loss. You really want the solution loss to be lower and to satisfy the constraints. Yeah. Okay. So finally, I'm going to class 3. I'm not sure people are already tired. Questions? Yeah.
Led to design choice of using linear program as the optimization, solving like
Yeah, exactly. Yeah, of course, linear program is much faster, right? Much faster to solve, and the quadratic may be very slow, maybe 10 times, 100 times slower, right? And in many cases, I don't think you can actually leverage the power of neural networks, right? If a neural network already can predict some corners that is good enough, then you don't need a quadratic program. Yeah, so there's a trade-off. Usually, like I think the point here is that this framework works for any arbitrary solvers and arbitrary neural networks. So if you want, you can play with different combination of them and find which one is the best. Yeah.
We got about 15 minutes left.
Oh, 15 minutes left. Okay, cool. Okay, good. Okay, so I have the final part. This kind of replace all with the models. That is actually a very interesting collaboration with antenna group in Matter, and we are trying to solve linear part differential equations. It's an interesting experience, and I'm actually one of the first authors of the paper derive all the equations, and I learned a lot of different IPD stuff. So for this one, okay, so I think people, especially people in academia, they like a lot about AI for science. So for AI for science, there's a lot of linear PDE problem you want to solve. This include heat equations, Schrödinger equations, Maxwell equations, etc. So these are very tricky to simulate accurately and efficiently. So can we do better? So the background of this problem is the antenna design problem. So in this problem, what we do is that we have a design kind of like a two-dimensional image for as a design of the antenna. So two-dimension basically say that which part you should put the metals, which part you should put with isolated materials, etc. And with the design, the goal is to make sure that the final frequency response has to be in some specific forms. So that's basically the design problems, right? So you see there's two dips here. The two dips basically correspond to strong absorptions at the specific frequencies. Right? So we want the antenna to be super strong in absorption for 2.4 gigahertz and also like 5 gigahertz-ish, right? So you want the antenna to basically absorb these signals in these two frequency range. So in that case, you really have basically an inverted design problem. You finally figure out what is the best edge so that the final frequency response look like that. Right, so it's something that nonlinear optimization problems. But one way you can do that is that very simple, right? So you start from simulating the design of antenna. You can try different approach of the design and use some simulators. The simulator will tell you, given the design, what is the best, what's the frequency response correspond to the design, right? So it does a mapping. And once you have the mapping, then you can basically find, okay, which mapping fit to your actual design goal very well. And then you come back and check, okay, this is actually the best one you can go, right? So very simple. But then the question is like the simulation is slow. So you have to go through like numerical simulation. You have to go through from CST solvers, and it may take some time, maybe 1 minute, 2 minutes. For complicated design problem, it might take like even hours in order to get the actual frequency response. Yeah. So this is actually very slow. Then what we do is that we can actually derive some kind of theoretical structures of this kind of mappings, right? So for linear PDEs, it turned out that there's actually a theoretical parametric form for the inequalities that is appearing in the Fourier transform of the equations, right? So for any linear coefficient B1, B2, so this phi hat is basically like any field that is transformed by a Fourier transform, and as long as they are linear combination, the ratio of them, if you consider ratio of them, then this ratio actually will look like the following, right? So it actually is a polynomial, and it's actually a rational polynomial structure. So it will be the division of two polynomials. Because the division of two polynomials, you can actually write them down according to the basic fundamental theorem of algebra, right? So it will be decomposed into zeros and the poles in the product forms. So you have to have these kind of structures for any linear IDs. So because you have that, then what we do is like because the antenna coefficients S11 can be written down as also quadratic, so some kind of like a quotient form, right? So with these two terms, and each of the Z here is the impedance, and which is also the quotient of the voltage and current, and the voltage and current. These two are actually integral of the field strength in the linear dynamics, right? So everything seems to be aligned with the condition of the theorems, right? So everything is linear, and it's quotients of the two linears. So because of that, you can assume that this S11, if you take the log, it's actually can be decomposed into this kind of structures. So you have zeros, and you have also poles, and then you also have the coefficients. So for all these three numbers, we can actually predict these three numbers with any neural networks that you want to use, right, from divine traces. By doing that, you actually automatically get rid of the simulation and can come with a good surrogate cost for these design problems, right? So then what we do here is that we start from some image-based representation of the designs of the antennas, and then we going through some transformers, and it will basically directly predict C, Z, and P from these transformers, right? So that's very simple. And once you have that, you can use existing data sets to fit that, right? So you start with some existing material commercial simulators, and given that you have a pair of H and the final S11, so you have a mapping. So the mapping may be expensive to get, but after you run a sufficient round of simulations, you might get, like, for example, a data set of 48K. Some data set that's maybe very expensive, but still fine to use. Then you can use the data set to fit to the previous transformers so that you get surrogate models. So I think here's I will basically, so this is the visualization about surrogate models. So this CZP model that we developed actually has a much smoother frequency response compared to the model that does not respect any of the smooth properties of the frequency response, right? So if you just predict this one using any arbitrary neural networks, then what you see is you're going to have all these humps. Right, so that's not smooth enough, but our approach, because we follow the linear PD structure, it actually gives you much smoother frequency response after prediction. So in terms of performance, we actually do two different evaluations. One is called a static evaluation, which means that you just test what's the loss in the test set, right? So basically, like, you want the loss to be small as possible, but you also tested the dynamic evaluation, which means that we already have this surrogate model. We can use the model to search a good design and see whether this design is really good in the practice. Yeah, so in static evaluation, we really see that, first of all, we find like the transformer actually helps a lot in terms of the loss. And second, we find that we should be able to use the CZP architecture compared to raw architectures. Because if you compare the raw with CVP, you see there's a gap between the two ones. Yeah. So and for CZP, there's coefficients, which is how many roots, how many like zeros and poles. Right. So this number is hyperparameter into 2. But overall, it seems like the loss is reduced, which is good. So, and finally, we can also do dynamic evaluations. So we can use CEP model as SurCo model and couple with search. Here, search, we just basically do a very simple reinforcement learning search with these value functions as the CEP models. And we are able to find that the percentage of success in any of the top 3 design is actually much higher than the raw models. Okay, so that's pretty much it. If you have any questions, let me know. So hopefully we still have some time to answer questions.
All right, thank you. Any questions from the class? Maybe they want to know what it thinks the internet meta.
Oh, okay. I think it's okay. It's a tricky question. I think it's
I do have a question.
Yeah.
So this kind of design this kind of work still requires a lot of, I guess, modeling work with a domain expert. One of the, I guess maybe one of the advantages of using LLMs and large language vision models is the opportunity to streamline significantly that aspect. Have you thought about that at all?
Yeah, so I think this is something that I forgot to mention in talk, but that's a perfect question to connect that. So first of all, people may say, okay, this is deep models. Where's the LLMs? Right. So I think LLMs can definitely be inserted in many different places. Right. So for SurCo, what happened here is that if you check their formulations, right? So the formulation, SurCo prior. So you can see like the formulation here. So this Y is the code description. But if you can imagine that this one can be any kind of and this Y can be any kind of descriptions in terms of text. Right. So once you replace this Yuandong with any kind of large models, then what happens is that you want to describe a problem using a text language, and it will basically get processed by LLMs, and that LLM can give you some coefficients. Coefficient can be used for some point. Right. That's the first way you can deal with that. So
the last chapter you talked was replacing the solvers with deep models. The domain that you gave was kind of very specific to the antenna problem. What do you view as the steps or the obstacles to replacing? Because for the first 2, it was very arbitrary. The problem.
Exactly.
It's like a specific set of constraints. What's getting in the way of replacing the solver here arbitrarily with a deep model?
I think first of all, I still think like the solver can be pretty important, because deep model right now cannot still give you precise solutions, especially when it comes to computing. Right. So I think that first of all, you put a solver there, and then you can solve the problem. That's good. And second, in the long run, if you want to completely replace the solver, then there could be a lot of challenges. Right. So one possibility will be obviously you can replace the solver, you can generate lots of data from solver, and hopefully the data can be very useful for training models. That's definitely one way. Right. So people talk about synthetic data all the time, and this is one way to generate something. That's definitely one way. But in the long run, what should we do is that if we can understand what's going on in transformer training, then we might be able to understand what it can do or cannot do in finding efficiency. Right. So in that case, there could be maybe like a more deeper integrations between solvers and systems.
Any last question?
Yep.